right now.
Okay. Good morning, everyone. Welcome to another edition of the Relatorium Seminar. This time, I'm very happy to host two of my collaborators, Mike Titelbaum and Owen Bissell, on talking about a piece of work that we just finished about a month ago. It feels already too long. We already have ideas for changing it, but and my hope, as I was just telling them before we went live, is that this is going to demonstrate a little bit sort of what happens, under the hood, like why we got together to work on this, how we make sense of it together. We bring different perspectives, and we want to keep it a conversation, basically. So please feel free to raise your hand, and interrupt the conversation if you want to contribute something or ask a question. We want to keep it informal. So without further ado, I'm going to start by sharing my screen. So the talk is about this paper that we wrote, which is called Topological Obstacles to Shared Priors.
Okay.
Yeah.
We're good.
Okay.
Yeah. You made it look like I wrote it. I didn't write it by myself.
I know, and I was just gonna say that. Thank you for saying. So my goal for foregrounding, Mike. So maybe Mike, you weren't here when I was telling Owen that you're the philosopher of our group, and I'm very proud. And I think early on we even talked about it. This is about 2 years worth of work that we really wanted to do whatever it took to make sure that we stayed in collaboration with a philosopher, because we wanted to have our work be meaningful to a broader audience than just a bunch of mathematicians doing technical things. And ultimately, also over the course of this collaboration, which I said lasted a little over 2 years, or around 2 years now, was a book that Mike wrote maybe 12 years ago?
Yeah, 2013. Yeah.
2013. And Owen, who is also here with us, actually read that book first before me, and had some thoughts about it. And he came to talk at JMM 2 years ago with some thoughts about that. Basically, he wanted to push back. There was some error, or he's going to tell us a little about that. Maybe, yeah, Owen, why don't you pick it up here?
Yeah, sure. So I wouldn't say that I found an error or something. I just found something really interesting in what Mike had written, where he was describing a condition for two people with possibly differing beliefs and possibly differing sets of evidence to nevertheless be in agreement with each other. And to my eyes, it looked really similar to the compatibility condition for a sheaf. And so I had the question, well, do these things form a sheaf? And then the answer turned out to be no, and it was super interesting. And the reason is that there are these topological obstructions to being able to patch together different people's beliefs to make one coherent whole. And the first project that I presented, at which a mutual friend of Mike and I's was there, and so that was convenient. But that original presentation was about a very specific situation in which you could nevertheless say, under these circumstances, all the compatible agents will be able to make a coherent prior together. And then this paper was about finding not just a sufficient condition, but necessary and sufficient conditions. So that was very satisfying to do with the whole group.
Right, exactly. And I think we'll go into the more details of how that came about, but in some way, it really, I think all along, it was, I think, a process of, for me anyway, opening my eyes to new possibilities. When I first heard your talk 2 years ago, I had some thoughts. Superficially, some of those thoughts ended up playing out, but in ways completely unexpected. And I think, even just as you say, there are these topological obstacles, for example, that appreciation, that realization arose organically over the course of 2 years. We didn't know what kind of obstacles, if there weren't going to be any obstacles, and what kind of obstacles there would be. And we weren't looking necessarily for this type of obstacles. So I think I intend this as an example of a kind of research which, by bringing together people from different backgrounds and asking different questions, it really energizes an exploration. It wasn't like we knew what we were trying to prove and we just set out to prove it. We didn't know. We had a sense, and probably diverse senses of there being something, but we didn't know exactly what it was. So anyway, with that in mind, and by the way, these slides, they have QR code and so on. If anybody wants the slides, they can just take them. Thank you. Okay, so here we go. This is the paper. This is the link to the archives paper as well. I'm not going to do that, but it is a link. And this is just the little abstract, which is more or less what Owen said. So let's. All I have in these slides is just the setup. And in fact, probably even the setup would require some conversation. So I don't want to rush through it. I do have some examples if we have time or if we're interested in going into the examples, but mainly the setup, because I think there's a lot to be said about why we chose this setup and how to understand the result in this setup. So we're looking at, as Owen said, a collection of agents, and the question is, they have different beliefs about the world, and we want to formalize a way for them to reconcile their beliefs and come together and sort of agree on something. But what kind of agreement could they arrive at? And of course, we weren't the first ones to do that. So perhaps maybe Mike can say a few words about where the philosophy background of this is. Like,
do we want to get to the point where you're talking about the priors, and then once you hit that,
okay, so maybe I'll get to the next stage. Yeah. Okay. So essentially, we're imagining that these agents at this point are endowed with credence functions, which are basically probability measures on some measurable space, and that all these probability spaces are subsets of one common space. And those subsets, A sub I corresponding to agent I, are basically the set of all possibilities that they consider of the possible states of the world. So we are allowing for the possibility that there are instances of things that some agents expect as possible and others don't. And those cases won't matter so much, because if anything, their agreement will only be possible in places where they both think are possible. If that makes sense. So we're looking at their overlaps, the places where these are the subsets where both agents think, or two agents, let's say I and J, both agree might be possible, and we want to assess how likely they are. And so the question of compatibility, which is what Owen mentioned earlier, the original question, when might two agents be in fact compatible? This is a form of concordance, if you will, of agreement, is if their respective conditional Bayesian conditional probabilities match. And what I mean is, for any subset B, any possible event in their jointly, comprehensible set of outcomes, their respective probabilities relative to the restrictions of their measures, of their credences on the overlap are equal. And then we want, and the third part here is to generalize this, essentially, to say, okay, if you can have this as a criterion of concordance between any pair of agents, what happens if you have a whole collection of agents, like capital I was the index set for the whole collection of agents. And here's a form of generalization that is apparently fairly common among philosophers. This is, I'm going to rely on Mike momentarily, but just basically, this notion of the existence of a prior called an prior, which is a one probability distribution such that the individual credence functions of all the agents are just essentially restrictions of that one big probability distribution on the respective subsets that correspond, that represent the individual agents' set of possible outcomes that they're considering.
Shall I jump in at this point? Yeah.
Right. So I was going to say, the question is, does it always exist? I mean, given the individual, beliefs of the agents, how do we know that they might have come from some joint prior? And so I'm describing it mathematically, but also, what does it mean, Mike, from looking at the agents as humans, like as the, casting in the sense of what we know?
Good. Okay. So there's a whole, for those of you who don't know, there's a huge movement in philosophy now to think about agents and their opinions in Bayesian terms, right? And to think about agents as having these credence functions that are probability distributions over some space. And over the past couple decades, there's been a lot of discussion about what it is for people to agree and what it is for people to disagree and the different ways they can disagree. Perhaps motivated by a lot of things that have been happening in broader society, in which we try to understand what disagreement is and what it would take to get a bunch of people with very different viewpoints to agree with each other. And you can imagine why that has become an ever more pressing problem. And one of the things that's emerged is, if you find two people who disagree, if they have different opinions about some particular matter, they assign it different credences. There are a couple different explanations for why they might disagree. One reason they might disagree is they have different information, they have different evidence, they've learned different things. And it's pretty obvious and clear why, if two people have different information, they would have different opinions about what's going to happen. Stupid obvious example, if you've got two people playing a game of poker against each other, each of them is making a prediction about who's going to win the hand, but each of them is making it based on they can see their own hand and they can't see the other person's hand. So there's a really obvious explanation about why they might have different probabilities they're assigning to who's going to win the hand. Each of them has proprietary information. Okay, that's an interesting thing. It can be well understood in a Bayesian framework. But there's another potential source of disagreement. The other potential source of disagreement is sometimes two people looking at the very same evidence, the very same information, can draw different conclusions from that evidence. And in that case, philosophers tend to say that those two people have different evidential standards or epistemic standards. And what the epistemic standards are how you process your evidence and draw conclusions from it and assign your credences on the basis of what you know. And sometimes when you run into disagreement, the disagreement is coming not just from the different information people have, but the different ways they have of processing that information. So then if you're a Bayesian, the question is, okay, how can we represent that mathematically?
May I interrupt, Mike, for a moment?
Yeah,
just again, for people who haven't thought about it as much, is it correct to say that when you're describing the different ways of updating their information from the evidence that they gather, that one type of that, just so people have a concrete example, is being Bayesian, is using Bayes' rule to update. But that is only one example. In principle, you don't have to be Bayesian. Is that correct?
So one question is, what's your update rule? Every time you gain new information, how do you change your opinions in light of that new information? And the Bayesians have a very specific update rule. You take the conditional probability based on what you learned. But even among Bayesians, even among people who are all using the same update rule, they can reach different conclusions if they had different starting points. And that's where this notion of an prior comes in. What you imagine is, and this is obviously a little bit fictional, you imagine every Bayesian agent starts their life with some distribution. And then they're going to update in the Bayesian way every time they learn something. And later on, they run into a friend and the two of them disagree. Why do these people disagree? Well, it might be one of them's a Bayesian agent and the other one isn't, but imagine they're both Bayesian agents. It might be one of them has information that the other one doesn't, but it might be they're both Bayesian agents. They both have the same information, but they started life at different places. They started life with different priors. And one of the reasons this can be really important is you ask yourself, how do you repair disagreement? The most obvious first step you make when you find someone you disagree with is you ask if they know something you don't, and you share your mutual information. And so a lot of the time when you run into someone you disagree with, one way to repair that disagreement is just everyone shares all the information they have. If these people are both Bayesian agents and they started with the same prior, then when they share all their information and they update, they will come to agree with each other. And that was the thing that was on the last slide. That was the condition Ted had on the last slide for if these people update on the same thing, right? That B right there. If they update on the same B, they will eventually reach the same point of agreement. That's going to happen if they shared a starting point, if they shared an prior, right? And so, first
So
of
by the
all,
way,
yeah, go ahead.
Mike, let me just say, so thank you.
Yeah.
I think you couched it very nicely.
Right.
But I must say, and I don't know if others have had this experience, but for me, I've always been slightly annoyed at this question that comes up in Bayesian thinking. And I think even I started getting annoyed with that even before I appreciated that its need and sort of the foundational role it plays within Bayesian thinking. And that is that it requires for you to have how you put it, like to have a starting place, right? To have an initial credence about anything. And what I have in mind is in scientific settings. Usually in scientific settings, people who consider themselves, sort of physicists, let's say, that they, or quantum physicists or whatever, that consider themselves Bayesian. I mean, they have to explicitly state that they consider a priori, before any evidence, the set of all outcomes or the set of all possible theories or whatever to be, equally likely or something like that, uniformly distributed. And so in some ways, I was annoyed. I was by that, epistemically annoyed, because you're like, well, why are you favoring one set of one measure, than another? It seems that you're putting something in by hand, and especially as it might make a difference in the end. There is no convergence theorem that says over a large class of priors you'd still get to the same thing, to the same result. Yeah, I was troubled. Is that a thing? I mean, do people complain
I mean,
to
first of all, there are
Bayesian stuff?
convergence theorems of exactly the kind you just right.
Ah,
But yes, philosophers have been complaining about this since the time of Carnap and probably even earlier, so for decades. And so the way most of us look at it nowadays is we don't actually think you start life. We don't think you're born and in your head is a probability distribution over every possible, set you might ever encounter. That would be David Lewis, very prominent philosopher, once joked about the super baby. And the super baby is a creature who's born and has a full probability. No one's like that. So the way we think about it now is you look at a particular agent and you see how they're thinking over time. And what you can do is you can construct an prior that models the opinions you see them assigning, right? And so really from a mathematical point of view, it becomes this interesting thing of if all you can see is the credence distribution at a given time, or maybe a few credence distributions they've had over time, can you construct an prior that matches what they're doing? And then interestingly, what if you have two people? Can you construct a single prior that matches what they're both doing? And this is where I started working with Ted and Owen, because then you get to this question of what if you have a whole set of people? Can you construct what are the conditions under which it is possible to construct a single prior that matches what all of them have been doing? And that's where the topology comes in, and it turns out to be much more interesting than I initially thought, right? Because this was the question that was in my 2013 book, because I was like, hey, what needs to be going on if you have a whole collection mathematically for there to exist an prior that matches what all of them are out there doing, such that theoretically, if they all got together and shared their information, they could possibly in the future come to an agreement. And that was just kind of a question, and I just kind of like speculated some things. And then Owen came along and he was like, this question's a lot more complicated than you thought it was. And then that's sort of where this all started happening. Yeah.
yeah. No, thank you. So let me go to the next slide to see what. Oh, Matt, did you want to add something?
I have something. Yes, Michael, you mentioned having the same or prior.
Mhm.
Is there a proof that it doesn't matter what the prior is, then the two agents always when they're updating on the same fact, they always come to an agreement? Or did you say that usually? Is it always or usual?
If you have two agents with the same prior, and they are updating in the Bayesian way, and they share all their information, then they will come to agreement. Always.
Okay.
But they have to
So,
share everything that both of them knows.
And the agreement, just to be clear, the agreement is the same credence function.
Yes, the same posterior credence function. Yeah.
so does that really take into account the following intuitive idea? What if both agents have the same prior that they will not come to an agreement?
So that could be either because they have they use different evidence, they don't share the same information, or they have different update rules.
Or like my dad used to say, they're just beginners. They don't want to come to any agreement at all. Neither one of them.
But then they'd have to violate one of these things, right? I mean, this is right.
Like what do they have to violate?
Well, they
share all their information. They both tell each other, we're never going to agree.
Yeah.
They share all their information, and they're both updating on the same fact.
So,
and they're never going to agree. That's their prior is, I'll never agree with you on.
So
I
good.
see.
So
I
here it's like, I don't know if you've ever read The Phantom Toll Booth, but there's the Mathemagician and the King of Dictionopolis, and they're brothers, and they had a fallout, and the only thing they both agree on is that they'll never agree with each other, right?
Yes, that's the kind of situation I'm talking about.
Good. Okay, so I think it's important to understand the theoretical role that the prior is meant to play. Here's the theoretical role it's meant to play. What the Bayesians imagine is that every agent is carrying around in their head a function from total bodies of information to credence functions. So every one of us is kind of committed to, if I had this total body of information, here's what my credence would be. If I had this total body of information, here's what my credence would be. And it's very important that the only input to that function is your total body of evidence. And so you are committed to, if this is my body of evidence, I'm going to believe these things, right? And it's a function, right? And what the prior honestly is for a Bayesian is it's just a mathematical way of writing down the values of that function. And so if two people share the same prior, what they do is they share the same function from bodies of evidence to opinions. And if two people share the same function from bodies of evidence to opinions, and then you give that function the same input for both of them, by virtue of the fact that it is their function, they have to reach the same conclusion. That's just
I'd like to thoroughly believe that. And so would, and similarly, mathematicians thoroughly wanted to believe that it would be possible to create a finitary reasoning system to prove the consistency of Peano arithmetic.
No.
Yeah.
So
and
I mean,
Gödel used a diagonal argument and a liar's paradox kind of situation, which is similar to what I'm trying to bring up here, to prove that logically that won't happen.
Yeah. So I think I would interpret that as meaning that that function that Bayesians imply always exists in the mind of someone might not exist. It would be the case that you cannot construct a consistent function that would do that. If you allow this,
actually proved that functions exist that we can't compute, right? But basically, that's kind of where this goes, right? And in fact, this leads to there exist functions that we can't ever say are functions. We can't tell are functions.
So look, there's a very stupid flat-footed answer to your question, and then there's the much more interesting answer, which is what you're getting at. So the stupid flat-footed answer to your original question is, in the situation you're describing with these two individuals, they don't have the same prior. It is not the case that they both have a function from evidence to opinion that is representable in this way and it's identical. That's the stupid flat-footed answer. The interesting question you're asking is, hey, are actual people like this? Right? And
I think there are people actually like this.
Yes, but not everybody. Yeah.
Right. And see, I'm playing devil's advocate right
Yep.
now as well.
Of course.
But
Thank you.
Yeah.
Part of what I'm trying to suss out is I don't know a lot about Bayesian inference. I know a little bit, very little. And there may be a big difference between the theory of Bayesian inference and the practice.
Yes.
I expect there actually is.
Yeah.
Because there's a big difference between mathematical statistics and practical, everyday statistics, the practice of statistics.
Yep.
But that's the question to some extent is, what are these events, the B's, and what are the A's? Okay, those are events, right? And so if those events can be mapped to a meta cognitive idea, which is similar to what Gödel did, right? He converted the notion of what does a mathematician do into an arithmetic system. And then that arithmetic system was part of piano arithmetic, right? And then because of that, he was able to formulate in piano arithmetic the statement, I am lying, or I am not consistent.
Yeah.
And how come there's no such function that could be had as the Ur-Prior for the?
So, for example, what you're imagining, Matt, seems to me to be, now I understand better. Maybe that could the set of outcomes that the agents consider as possible, like the AIs, refer to the agents themselves, refer to each other's beliefs, for example. That's a good question. It's not what we considered specifically.
Yeah, there
yeah.
So it's also, but that kind of reference between two agents can be converted into self-reference for a single agent, right? In a natural way,
right?
Which is very close to what I'm headed for.
Yes,
what I was asking about.
Accommodated. So we didn't mess with this. And by the way, Irfan, you've been waiting very patiently.
Yeah, I know. I was going to say, please.
Oh, I'm sorry. Okay.
It's fine. Do you have something on this, or should I sort of address what Matt just said?
No, I was going to go further on what Matt was asking, because I guess the conversation already started going in that direction, because I was wondering how would you even formulate such an R-prior? Like, does your measurable space allow formulating such an R-prior where the R-prior says you will never agree? I'm not sure how to formulate it.
Yeah, so
part of my question is, what in the Bayesian theory prevents the construction of such an R-prior?
Nothing. So the framework that Ted and Owen and I and our other collaborator have been working in, just as a start, doesn't incorporate that sort of thing. I will say there are philosophers and statisticians who work with spaces in which you can say things about what are the credences other people are assigning and what are the credences you're assigning. So there are probability theories that incorporate higher order probabilities. And some of the higher order probabilities you can incorporate are probabilities about your own first order probabilities. And there are results about this because you're going to have these sort of fixed point issues where if your higher order probabilities don't mismatch your first order probabilities in certain ways, you get breakdowns. There's a very famous paradox having to do with this, which is not too far from the sort of Gödel paradox you're talking about. And so there are theories that, first of all, represent these sorts of things inside the space of possible events. And then there are various proofs about sort of like what kind of boundaries you've got to put on that to keep the whole thing from falling apart very, very rapidly, for exactly the reasons you were just suggesting, Matt. So it's not a thing that we've been doing. It is a thing that there are these things called probability frames that are, anyway, there are structures that can be, yeah. And boy, do I have some conferences I'd like to invite you to. but yeah, there are.
Yeah, if you can pay my way, I'm retired. So.
So yeah, no, so I mean this does so at some point in our collaboration, as we were looking for directions to take it, one of the things we were interested in, because I was coming more from a categorical perspective as well, was to question the whether everything in conditionalization boils down to or can be accomplished within the monad structure of probability measure of like a simplex and so on. And in other words, this is something that I had in mind exactly at the time. This is now over about a year ago or so when we were talking about those things. In other words, other ways in which you can, more than a year, what am I saying? Year and a half at least. Other ways in which, like, as we say, the probability of a probability cannot be reduced down to the same level probability, but they're layers basically, and the sorting matters, who is doing the talking, and they're not necessarily exchangeable and reducible one to the other. It's beyond the scope of the paper, but I'm glad it came up. Irfan, do you have something more specific in mind?
No, my specific question was exactly the technical question of how you would construct such an outlier that would express such a statement.
Hmm.
So
I mean,
it was more like
practically,
a language question. How would you express such a statement probabilistically?
So there are practical considerations. Well, practically, let's just say people disagree already before that. So our interest was to say, even in simpler ways, when people disagree, how can it come about? How can we demonstrate that they in fact might agree? Or what kinds of agreement structures? So the low hanging fruits in the possibility of agreement structures, right? But in reality, there are these deeper ways. Like they might disagree in more fundamental ways, and in ways in which the existence of an prior might not be the way to demonstrate or to bring about a possible agreement. This is again a direction when in last year's in the 25 JMM, I spoke about a possible framework that I've been thinking about that, and this is one of the extension ideas that we have within our group. Maybe we should postpone the further details on this until the end when we kind of talk about the extensions.
Yeah, and I just put in the chat, if anyone's interested, a kind of representative paper that shows how you can build one of these higher order probability structures that Geifman published in the 80s. So if you're just curious about how you might build such things into the event space over which probabilities are defined, that's one way to do it. There are plenty of other ways to do it, but yeah.
So the fact is that, and Owen had to leave, unfortunately. But the fact is that Owen discovered this very curious and unexpected structure that happens even when we don't consider those. So in other words, there's already secret depth to even the simplest of cases as we set it up. So we kind of set it up in a way that excludes more, like tries to get it to a simple heart of the matter. And even here, there's this surprising, unexpected depth. And so that's, I guess, where we're going with this. And to move basically, where does the topology come from, right? Like the idea is that there is a simplicial structure among the agents that describes, and some of you may know this or may know something analogous to this, not exactly the same thing technically, but something analogous to this, which is the nerve complex in sort of topological data analysis. But so this is essentially a simplicial complex that looks at the overlaps between the subsets that represent the agents. In other words, the sets of things that the agents consider possible. The main importance here is that we want them to assign positive probability to them. Right? This is a technical requirement because of the Bayesian setting in which we are, because in Bayesian settings, we have to divide by the probability of the overlaps. So for example, if agent I and agent J have a non-zero overlap in their in the set of possible, there are some outcomes that they consider, both of them consider possible, and they both assign non-zero probabilities. Then there is a one simplex that connects it. There's an arc that connects those two agents. So the agents are like points or nodes, and then you create this simplicial complex structure. And the interesting thing, the surprising thing, is that the cohomology of this simplicial complex plays a role in the existence of or prior, but in subtle ways. And there's nothing probabilistic here, right? This is only about the, if you will, the sigma algebras, not the credence functions. Okay, so here is basically our main result in words, right? So if we have an overlap simplicial complex for a collection of agents, right? Essentially, that is just a representation of the combinations of outcomes that they consider possible with non-zero probability to occur, then these two statements are equivalent. The first statement says that pairwise compatibility among the agents is equivalent to the existence of an error prior. And in particular, the point is that pairwise compatibility implies the existence of an error prior, because the other direction is trivial, right? So they can be, if they're pairwise compatible, then they're all compatible in some sense, in the natural generalization of compatibility. So that's one statement. The second statement is that the first cohomology of the simplicial complex vanishes. And so this is surprising in both directions. And so we have examples to demonstrate that. In other words, both in the positive and in the negative direction.
Can I just
I mean, at this point, I want to open it up.
How surprising this is, Ted? Can I just explain my emotional state when I encounter
Please, yes, please.
Yes, so we've got this question that philosophers have been talking about, which is, what does it take for a whole group of people to kind of see the world the same way in a really basic sense, right? And that's this notion of compatibility. And one question you can ask is, what has to be going on with the group such that the whole group seeing the world the same way boils down to each pair of people in the group seeing this world the same way in a certain sense? And that seems like a very sort of natural question. Like, if each pair of people could come to an agreement, does that mean the whole group can come to agreement? And initially you might think, well, yes, obviously. And the answer is no, not obviously. In order for pairwise agreement to lead to whole group agreement, there has to be a structure among the space they're all entertaining. Oh, okay, what's the structural requirement? It's a topological requirement about cohomology. That was just like totally unexpected and blew my mind, and I didn't.
To be even more explicit, I'm so glad you said that, Mike. And to be even more explicit and historical here, my involvement in this study 2 years ago, when Owen in the JMM was presenting a situation where he was saying, in other words, no, it's not necessarily the case that when the agents are all pairwise compatible, that they will all be compatible, because, and in his case, he was demonstrating you need to have a set of some set in the overlap that all of them assign non-zero probability to.
Right.
And if you didn't have that, it would have essentially boiled down to, we didn't know it at the time, we didn't describe it this way, but essentially it would boil down to a non-trivial first cohomology of the overlap complex. Okay. And I said to him, I get that, but I think that's in a way the simplest case, because I said, well, of course, in some intuitive sense, of course, I didn't know, I was being a little, oversimplifying in my mind, but my intuition was to say, well, of course, if they had a set where they all agreed, I can imagine how, and they assigned, meaning a set over which they all assigned non-zero probability, even if it wasn't the same probability, I can imagine how you can adjust your priors in a Bayesian way to make them match afterwards, right? But what if there wasn't? What if their overlap was empty, right? And this is the not only no, but yes, in an important way. It turns out that all you need is the first cohomology. You don't need the second cohomology to be non-trivial. In other words, all you need are every triplet to agree to have a non-zero overlap. and that's sufficient for all of them. And that is surprising as well. So it's surprising both in the no on the one side and in the yes on the other side.
Ted, does it make any sense to think of that as being closely related to the fundamental structure of the definition of transitivity? Because
So
you're
we don't
looking
know
at a
for sure.
transitivity condition for agreement, right?
Yes. Yes.
So transitivity is like composability in category theory, right? So transitivity involves 3 elements, not just 2.
Right. Yes.
So
but how can you? Yes. Yes. And the question is, why don't you need more
this
than
fits in the topos concept because it's like a topological condition on your logic, right? So
right
on your
and
reasoning
so,
system.
And so you see why when Owen was thinking sheaf theoretically, that was not, it was a pre-sheaf, but not a full sheaf because of this. So you need a higher topos construction to incorporate this possibility. The possible non-triviality of higher order cohomologies, but not of the first cohomology in some sense. So it's like it's a tiered thing. There is a structure, as Mike was saying, there's a non-trivial structure that needs to be in place. That was not accessible in simpler terms. In some ways, you needed to understand it topologically, or at least to us, it feels like it wasn't intuitively obvious. Now, after realizing this, and it took us, as I said, a couple of years, we've been trying to find better ways to describe it, right? To know why is it. Owen does have some thoughts about this, and this is a possible area of further direction of work in terms of something to do with the restrictions that we put in place. We put in place the simplest, most restricted setting. In other words, they all have Bayesian update rules. Their agreement is an equality, right? They have to exactly agree, and the assignment of credence is everywhere. It's not on average. It's not it's not a weak statement or whatever. But we don't have, we haven't arrived at a good intuitive understanding of why that is. I mean, obviously the transitivity plays a role, and it's the question of compositionality of transitivity. And I mean, you can see it algebraically as basically constraints on the joint solutions of systems of equations. The systems of equations being the qualities of the respective conditional probabilities. And in certain cases, it just says that solutions don't exist. Solutions exist in subsets of equations, but not in the whole set of equations. So something of this kind. So it has an algebraic aspect. And in fact, as we were writing the paper up, one of our other collaborators, Colin, found a strand within the literature within the literature of algebraic statistics. The approach of Bernstein-Fels and some of his students who had done some work on this, again, about 10 or so years ago in the early 2010s, I think, which is entirely algebraic, not topological, right? And in terms of these varieties that represent sets of solutions to systems of equations of the kind that we're talking about. And it turns out there are some other strands of work relating to the mutual compatibility of conditional probabilities. But ultimately, no one had answered this particular question, and certainly not in this concise way. So we kind of felt that our diverse perspectives of how we came at it from just, I guess, maybe more philosophical or practical considerations afforded us the space to think a little more open-endedly. And anyway, we're proud of this result. At this point, we have some examples. I mean, Owen again was really nice. It came up with an example that comes from metallurgy, and if we have time and if people are interested, just to kind of make it concrete, I can show you that. But I only have one more slide before that, which is basically this slide about 2 main directions for future work that we have explicitly talked about. There are others. These are just an attempt to kind of organize them. And the first one, well, let's say the second one The second one says, well, what if the agents have different update rules? We already talked about that. What if they're not Bayesian, right? What if even starting with the same prior and with the same evidence, they just updated different? And this is something we have thought about, and it's quite interesting. There's reasons to think that perhaps the geometry of the simplex, the probability simplex will play a role. But anyway, that's it. It's open-ended at this point. The first one we haven't talked much about, so I just want to mention this is one that I particularly was very interested in, which is what if the sigma algebras that the agents come with differ? Until now, we were talking about each one being a subsigma algebra of the total. There exists some overall sigma algebra for the whole set A, and they each kind of only see some portion of it. But what if they're mutually incompatible? And one way to think about it is, what if they have different languages to describe the world, right? In other words, different levels of specificity about the subsets that they see in the world, and they're only partially translatable, because they have overlaps that they don't see, for example. And so in what way could we describe a form of agreement nonetheless, despite the difficulty of communication? It could be that you could make only very coarse statements. They will only care about agreeing on things they both see or they all see, which would be a very small subset of the world. Or, which is more hopeful, the second statement here, possibly find ways to combine their sigma algebras as a sort of an algebra of sigma algebras to create a new one that is finer than any one of the individual ones could be. So they could help each other come up with a common sense of new things that they didn't any of them saw as possible before, like a product structure or whatever, some other kind of structure. And I am thinking about categorical structures, on the space of sigma algebras that could allow us to proceed. Again, these are directions for future work. Mike, you want to add anything here?
Yeah, I mean, two things. Just one thing is sort of this bit about the other languages. One of the questions I asked in my 2013 book was, when you refine your language, perhaps by encountering another person with a different language, is there a sense in which you should keep all your opinions the same and just translate them into the new language? Or does the very realization that there are other possible thoughts to have that you haven't been having mean that you should rethink some of the opinions you already had? And that's a really interesting question, and there are a lot of ways to represent it. And then the other thing is, as we make all these generalizations, one thing that happens when you generalize a result is hopefully it helps you understand the explanation. So sort of looking at what Matt just suggested, is the fact that the first cohomology is so important, is that because of how transitivity works, right? Or could it be that actually when we expand into these further generalizations, it turns out the first cohomology isn't the important thing, and that points us towards a different explanation of what's going on, right? So part of the point is we want to figure out how this works in a wider variety of situations, but also now that we found a way that it works in this one particular situation, we hope that by broadening out to other situations, we'll learn sort of like what are the load-bearing features, and that'll help us better explain what the heck is going on. Yeah.
Are there any thoughts or questions, ideas? I do have the examples that I could start showing some examples, but if people want to take it in any direction, I'm happy to entertain here.
It seems to me to be a strong intuitive connection here to economics.
Oh yeah, I agree. And we do have references
computational
to some,
as well.
We have references to some agent-based economics, exactly, and who are very interested in this type of thing.
Yeah. So what's the term they use in economics? It's not a prior. It's I'm losing the word right now.
Not sure.
It's a preference.
I only hang out with Bayesian economists, so they talk about priors.
Is it preferences or?
It's related to preferences, utility? But I don't.
Utility.
A utility function. Yeah. That's what it is.
Okay.
I'm thinking that an or prior in an intuitive sense corresponds to utility functions in economics.
So in traditional decision theory in economics, we actually imagine every agent as equipped with two things. They have an prior that informs their credences, and then a utility function that informs their preferences over outcomes. And then you smash those two things together to calculate an expected utility. But there has been work on how people update their utility functions in response to new information. And all these questions come up again, right?
Yeah.
Right.
Yeah.
And in some sense, at a modeling a human perspective, from behavioral, perhaps the distinction between beliefs and utility is sort of more epistemic than in other words, it depends what you ask. But they're analogous structures. So perhaps they are looking at the same thing from different perspectives.
Yeah. And in fact, the kind of canonical way that economists approach this, at least historically, has been through revealed preference theory.
Right.
Where all you have is you look at the agent and you see what they do. And then you build a model where you pretend that what they do is a result of a credence distribution and a utility function, and they're calculating expected utilities, and that's what's making their choices. Right. But that's just an artifact of the way that we tend to model the thing. All you have is the person's out there doing things and saying things, and you got to figure out some way of pretending what underneath the hood is generating what you're observing.
Yeah.
Right. And right. So, I mean, and to build on that, that's exactly what I had in mind, Mike. Thank you for saying that. But to build on that, it is unclear if fundamentally we're trying to think of what a human is as an agent, if it really is useful, and at what point does it become not useful to try to separate what they believe with what they want. It's an epistemic thing. Like we can imagine, as you just said, let's think of humans as agents who have these two things. They have things they believe and things they want, and then what would happen in their interaction. But that there may be a limit to how much we can explain the world that way, and maybe it's important, it's useful, perhaps, and interesting mathematically to think of some other type of structure that encompasses both, where these two things are just facets of the same object. Because sometimes we say we believe something because we want a certain outcome, or the things that we say we want is because of what we believe the state to be. In other words, they interact with one another. They're not independent properties of the system. Okay, so since I mentioned I'll just start with showing the example, just so we have something concrete here.
And we should emphasize this is an example about metallurgy. If anyone actually knows anything about metallurgy, we don't know anything about metals.
Right. I think Matt might. I don't know, but yeah. So because Matt, I think, has a background in chemical engineering. So
that's right. We probably screwed all this up, but we just made up an example. Right.
Okay, so the example is that there are these metallurgists who are trying to figure out what a metal is, right? So there's the set of possible metals. I assume I think they are metals.
I think
there's 7 of them. Yeah, and then they have different evidences. So here's the idea: like agent 1, as you looked at the color, and based on the color, they've narrowed it down to these 4 things. And agent 2, has noticed that it tarnishes, and so they have these 4 things. And agent 3 has these other 4 things because it's a precious metal. Okay, so this is an example of the type of thing we're looking at. And in particular, here are their respective probabilities. These are basically arbitrary. We just did them this way so we can do the computation easily, but basically they're arbitrary. Okay, and now the collection of agents is pairwise compatible. So this is an example of pairwise compatibility, which means that if agent 1 and agent 2 were to pool their evidence, they would narrow down the possibilities to just silver and iron, right? Because those are the only 2 overlaps between the 2 of them, 1 and 2. And conditional on that, they each assign basically 3 to 2 probability that it's iron rather than silver. As you can see, like 6 to 4 here, 3 to 2, right? So they were engineered that way. And the same thing is true between 2 and 3 and 1 and 3. It's easy to verify. Okay, so here's the topological, on the left is sort of the set description of their outcomes. Here are the agents, right, what they consider possible, and they have overlaps. And in this case, there is a 3-way overlap of silver, right? And this is their overlap simplex, or simplicial complex, right, in general. and it's filled in, right? Because they have a three-way overlap as well. So this is a simple case. And of course, in this case, the theorem says there is an error prior, and here's the error prior. It turns out it's a matter of just computation to see that the individual agents are basically restrictions of this to their respective set of 4 possibilities. So in other words, if they all started from this and they happen to add the observation they made, oh, it's gray, then it restricts to the probability of agent 1. Oh, it's precious, so it restricts the probability of agent 3. This reference 6 here is the original reference that Owen, the paper that Owen had written and presented 2 years ago, where he was saying that, all they have to do is, so that the existence of the error prior is, can follow from pairwise compatibility and that there's a common event they all assign non-zero probability, namely in that case, silver. In this overlap, right? And that's where I said to him, look, yeah, I get that. That's good. But so, which means that, first of all, it's an answer to no to Michael's original question, right? Pairwise compatibility doesn't by itself imply the existence of the error prior. You do need the overlap to have a non-zero overlap, right? But I said to him, yeah, but to me, this seems trivial. This not trivial, but like I can get why that is. I can imagine why that is, because you're dividing by something that is guaranteed to be non-zero, so you adjust the probabilities. It was oversimplifying. The details are more involved than that. But I didn't see. I wanted to see what happens when there isn't. Is there ever a possibility where the error prior would still exist even if they're non-zero overlaps, right? And that was the start of this collaboration from my perspective. So then we came up with a modified example where, first of all, to see why the overlap. This is Owen's attempt to show why the overlap was essential, among the 3 agents. And he says, so here are, again, 3 agents. Now they have only 3. Each of them believe only 3 possibilities rather than 4, so their evidence is something different. And in this case, manifestly, there cannot be an error prior, because if there were, then you would get a non-transitive or cyclical sort of set of assignments. And this, by the way, Matt, is exactly the kind of thing you were talking about, the obstacle on the non-transitive side, right? And how it relates to utilities, because that is what economists care about, transitive utilities. Okay. So, by the way, here's the simplicial complex in this case, right? It's empty. In other words, it's just a triangle with non-trivial first cohomology, because there's no overlap in the middle. Okay. We have 2 more examples, basically to demonstrate the other side, essentially. Okay, now we consider a case in which the non-existence of an error prior implies that the agents cannot be pairwise compatible. Okay, so this it means that you see, because pairwise compatibility always implies the existence of an error prior always implies pairwise compatibility. After all, the error prior is the generalization, right? If it exists for 3 or 4 or 5, then certainly they must be pairwise compatible. And so this kind of says that if the error prior doesn't exist, then we know for sure you cannot make the agents pairwise compatible. So we go back to the previous example, the one that is not compatible, what I just showed you with the empty overlap. And we add a 4th agent with another 3 things, right? This agent plugs the hole in this way, right? So this agent now plugs the hole. And not only that, you do so in a way that, let's look at this, right? You cover you have overlaps with everything else, right? So in terms of, they didn't have an overlap amongst themselves, but you have an overlap. 4 has an overlap with 1 and with 2, a joint overlap here, right? So 1, 2, and 4, for example, overlap at iron, right? And 4, 1, and 3 overlap with platinum, for example, right? So literally, you see this as a 3-dimensional simplex, right? This corner 4 is up top. The bottom is empty. of this pyramid, right? Okay. So in some sense, so this is what this does, right? And these four agents now cannot possibly have an error prior because the original three agents didn't. So obviously, if say three didn't, obviously the four ones couldn't possibly have it. Which means that according to the theorem, this is our main theorem, it must be that they cannot be made pairwise compatible. So even though the original three had been pairwise compatible, the fourth one cannot be made pairwise compatible with all three of them. Because if it could, then they would have to have an error prior, but they cannot have an error prior because the first three didn't have an error prior. Okay? And you can actually, in this case, demonstrate it, by the system of equations that's basically inconsistent. Okay, in other words, you say, okay, well, what could be the probability, what probability do we assign among the three things for the fourth agent in order to guarantee compatibility? And this would be the compatibility, the pairwise compatibility with 1, 2, and 3, and they're inconsistent. So you can't make, as the theorem predicted. Okay, so this is kind of to show the power of the theorem on the other side. And by the way, sorry, over here, this simplicial complex, the bottom face is still empty. So it has a, you see what I mean? So in other words, or put it differently, this has non-trivial cohomology, first cohomology, but the fact that it has non-trivial first cohomology means that if you go to the main theorem, it is equivalent to the fact that it would only have an error prior if and only if it had if and only if they were pairwise compatible. And since it doesn't have an error prior, we know they can't be pairwise compatible. Okay. Finally, sorry. So at this point, it may seem that pairwise compatibility is equivalent to the existence of an error prior if and only if the subset to which all the agents assign non-zero probability, right? However, that's not the case because, in other words, the second cohomology doesn't actually matter. And here's, so now we go back to the original example, the nice one that Owen had made where everything worked, where they did have an overlap of the first three had an overlap, so they did have an error prior. And we now add a fourth one, right? And we add a fourth one in such a way that that it is pairwise compatible with the other three. And the three of them had an error prior, right? And now it turns out with this fourth one, you still get an error prior, even though, why doesn't it? Okay, never mind. So even though manifestly you can easily see that, well, I mean, you'd have to remember what the other ones were. We couldn't draw this. This would be a three-dimensional, like a higher dimensional drawing that you wouldn't see. But essentially, the overlap complex here has all four faces, right? But it's empty in the middle. There is no four-way intersect, right? So platinum, bismuth, iron. If you go back a few slides, sorry, if you go back to this nice example. Platinum, platinum, iron, and bismuth is what the fourth agent has. So it doesn't have silver, which was the overlap before, right? So there's no four-way overlap, right? But that's not necessary. The four agents do have an error prior, even though they don't have a set that they all agree on. Because they agree in triplets, all the triplets agree, right? So this is an example of why the second cohomology doesn't matter. It could be non-trivial and it doesn't matter. Yeah. So these are the examples. So maybe I should stop projecting here. Oops, and stop sharing and just look at people. Yeah. So what do people think? Matt, how was this example? Did it make sense?
I'm a little confused still, but
it is a little confusing. Yeah, I went quickly.
Because I guess I need to have a better idea what you mean by agree here.
Agree means that there is a set of outcomes that the agents assign non-zero probability to all of them.
Okay. Just non-zero, not the same probability.
No, not the same, non-zero. Right.
Okay, that's
And
not
then that's
full agreement in my view.
So there's two notions floating around, right? So this
yeah,
is
sorry, yeah, maybe
so
my
one
wording
one notion is, do they have things that they assign non-zero probabilities to? That's one notion, and that's the thing that is generating the structure on the simplicial complex, right?
Yeah.
That's determining what gets filled in and what doesn't. And then our other notion of compatibility is, are they such that if they were to update on the same thing, they would reach the exact same probability values, right? So that's the other notion of agreement. That's the like more demanding notion of agreement, right?
Yeah, yeah.
What we're trying to figure out is this basic structure in the simplicial complex that's just generated by what they assign zero and non-zero to. How is that interacting with their ability to agree in the more demanding sense? That's what we're trying to figure out.
So yes, thank you. And thank you, Matt.
Yeah.
Sorry, I think my wording was very sloppy, and when I said there's no set they agree to, I mean only agree to assigning non-zero probability to, not the same probability. So it's a very weak sense of agreement that would construct the overlap complex. And then to use that to prove equivalence of much stronger agreement, which is the compatibility assumption. Yeah.
Right.
Yeah. So if you modified this whole approach to measures instead of probabilities, then a 0-1 measure would be a weird thing for this. That's because 0-1 measure is used for logic, right? So where you have yeah.
I mean, it's maybe an instance philosophically, and I don't know if I'm overstepping here, but a little bit of, to me, it always harkens to a notion of epistemic humility, right? In other words, there's a difference
epistemic immunity. Is that what?
Humility. Epistemic humility, right? You never assign zero probability to, whatever you have. So this is one aspect on the boundary of things, right? That you never assign completely zero probability. You can assign low probability, arbitrarily low, but not zero.
Now, yeah.
But because that allows you to update it in a Bayesian setting. Now, if you don't consider a Bayesian setting, if you allow yourself to consider non-Bayesian update rules, this might not be as big a thing. So in some sense, it's a technicality because we restrict ourselves to the Bayesian setting. Another related sort of boundary issue, I say boundary in a literal sense, but in reality, it's important. I don't mean to belittle it by saying that, is the difference between assigning zero probability to something and simply having the thing not be part of your sigma algebra, right? And I know Mike has thoughts about that because it's an important thing within the philosophy literature. In other words, is it part of your language and you deliberately, explicitly assign zero probability to it, or is it not even part of your language? And so you have no way to assign any probability to it, including zero.
Exactly. Yeah.
I mean, if I was speaking like if I was speaking like a grad student, and I would say that under Lebesgue measure, every point has zero probability, would we not be considering points, or
exactly? No,
what's the issue?
Why it comes up. That's the first context.
Can you repeat that, Irfan? I didn't get that.
I'm just wondering what the philosophers are arguing about here, because under Lebesgue measure, all points have zero measure. So are they arguing whether we should consider points as information or not? Or
so there's
we never see point. There's never no evidence of points, right? That you could say there's only evidence of something that looks close to point, but there's never evidence of a point.
Right.
And that's exactly why there's a whole crew of us who think there's an important distinction between literally ruling something out as a possibility and assigning it zero. Because sometimes all the things we rule in as possibilities at the point level all receive zero, right?
Yeah, I wish Peter Loeb were here.
Yeah, unfortunately,
because he said that the big difference between zero probability and infinitesimal probability is something like the following example. If I aim at a target that's on a barn and pull the trigger, I have a if the target has a point as a bullseye, I have an infinitesimal probability of hitting the bullseye. But if I point my gun to my back, I have a 0 probability of hitting the bullseye. If I point it backwards away from the barn.
I like that.
So,
Right.
yeah, it's similar to conditional thinking or conditional probabilistic thinking, but you're conditioning on trying to hit the target versus not trying to hit the target. And that's a good way to explain to a probabilist why infinitesimal probability makes sense as opposed to 0 probability. And
So I wonder, yeah,
in this epistemic humility that you mentioned, Ted, epistemic humility might say, in a non-standard setting, we assign infinitesimal probability to almost everything, but then there are some events we assign 0 probability to because we're not actually going to ever see them from a logical or reasoning standpoint. They're just provably not possible.
I think what's happening is, at least among the philosophers, there is a general recognition now that there's a difference between ruling something out versus assigning an event a probability which is lower than any positive real number. And then there's a debate about whether the right way to think about the latter thing is to give it 0 or to give it an infinitesimal. And there are sort of partisans on both sides of that debate. Yeah.
Right. And if I remember our conversation about this correctly, Mike, there are some people who are philosophers who are interested in conditions under which we bring something back from 0.
Yes.
Which might make it easier if it's not
so just to be clear,
0.
ruling something out and then ruling it back in. So not just bringing it back from 0, but bringing it back from the even more dramatic thing.
Oh,
right?
Well, it's not even in a sigma algebra, and it's kind of
right. So here's a really stupid example, right? I just came from breakfast. We just had breakfast with a job candidate, and at breakfast I had hash. So right now I'm very willing to rule out that for breakfast this morning I had oatmeal. Right? That's just not even, I'm not even assigning that an infinitesimal. It just didn't happen, right? Well, a year from now, if you say to me, hey, what'd you have for breakfast with that job candidate? You know, oatmeal might be back on my set of possibilities I'm willing to entertain. So this idea that you could rule things out for a while and then for any one of a number of reasons have to bring them back into the conversation later is a live possibility. Yeah.
Now, this may be an absurd comment, but when you start talking about not being in the measure algebra in the first place, the sigma algebra in the first place, and then you bring it back in, you take it out and put it back in, and so forth. That dynamic behavior of your sigma algebra seems to me, or your approach, your view of your sigma algebra is what I should really say, because mathematically, to me, one of those is a different sigma algebra than the other. You're not changing the sigma algebra, you're changing which one you're using. It sounds a lot like the kind of approach that's used to study martingales, super martingales, and sub martingales.
Right.
Because you update the measure algebra.
Yeah, so this was my background when I mean, in the sense that when I was talking with Owen initially about it, I was and for a while I've been thinking about basically filtrations being one type of operation you can do on collections of sigma algebras, but I was hoping that you could do more interesting interactions between sigma algebras that would transcend what you can do with a filtration. And I mean, and that was the impetus behind the session we organized last year at JMM as a sort of conditionalization, categorical versions of conditionalization. In other words, lifting to what are things we can say about different update rules, like what are the desirables we can have, and how at what level can we describe them. And there's a surprising number of philosophers, I think, who, for me, surprising, probably not for Mike, I don't think, who have been thinking actually very seriously about these things. Maybe they lack the formal structures that mathematicians might entertain. Like, for example, we had some speakers who applied diagrammatic approaches to collections of sigma algebras and so on. And I'm hoping to, in fact, even invite one of them to a lectorium talk at some point. But yeah, I think how to formalize, these ways, just to return back to the beginning, like how to formalize different strata of possible agreements that apply to, sufficiently diverse set of agents. I think is very interesting and very applicable, and not just in economics. But Irfan, I think you had something to say. You were starting to say something, and we
No,
rudely
so
interrupted.
I have something to say, but it's that we have a rare question from YouTube chat. Uh,
Ah,
but I don't. So I'll have to preface the question, and I'll have to say more about it because I don't think we'll be able to define what the chatter is asking. But they're asking what is topology. So I don't think we will be able to technically define what is topology, but I think it is interesting because our audience is very wide in terms of scope, and so there might be people watching who might be interested in the practical probabilistic interpretations of your talk, but might not have any idea of what topology is. So
So
could you give
there
maybe
are
a 2-3 minute?
some real quick things you can say about that, Irfan.
Yeah,
Of
yeah. So
course. I
that's
mean,
the question. Yeah.
there's the technical definition that you can rattle off and that won't mean anything.
No, I think maybe it would be good to give an audience something about intuitively what is
Yeah,
topology and how it becomes relevant in this.
yeah.
so I think it has to do with a collection of structures and structural constraints between how subsets of outcomes can interact with one another. And so we are construing agents as basically collections of possible outcomes that they consider. And then the topology entails some sort of interaction between those collections of subsets. So there's algebra for that as well. But so there's probability. But in this case, topology is one of the weakest things that we can do on those sets of subsets. So we want to make as few assumptions as possible, but there's still structural constraints essentially. And we're bringing up a particular type of structural constraint having to do with overlaps. So that's why we call it topology. And there's a hierarchy of those, right? So they could be pairwise, triplet-wise overlaps, and higher order overlaps. And so, strictly speaking, in some ways, a question around that is, where we talking about. So we were talking about cohomology, which is a way of understanding topological constraints. It wasn't really trivially obvious in anything I said that it was cohomology and not homology, for example, right? So there are technical questions about what is it. So we're assigning functions, namely these credence functions, on the subsets. So we are assuming not only these are not just properties of the subsets themselves, but properties of ways of assigning a real number, namely a number between 0 and 1, in fact, to all those subsets in a consistent way that obeys the rules of probability. And so then it becomes a question of cohomology. In other words, how those functions can compose with one another over the overlaps. And so it becomes a question of talking about the structural constraints of the overlaps of these sets, like in a Venn diagram, but vis-a-vis with an eye on the real valued functions on them that have to obey probabilistic rules, essentially. I don't know if that's helpful. It probably is too technical still.
That has more to do with the second part of what Irfan said, I think, how topology relates to what you did. But it doesn't have as much to do with explaining to somebody who doesn't know what is topology. Because topology in general, like you have a space you want to work in, and for physicists in the late 1800s and early 1900s, that was physical space. You want to work in physical space, but you're working in a conceptual space. And the original term for the area of mathematics that became topology was analysis situs, or an analysis of our situation, or in your case, it's the computational situation, the conceptual representation space that you're going to work in, and it's the shape of space that we're looking at when you do topology in a lot of ways. And For physicists, it's the shape of space, and now physical space, and they've used gravitational fields and theory of relativity, general relativity, to say that space curves. Well, now the shape of space is determined here by your computational constraints and your conceptual constraints for Bayesian inference and such. That's my understanding
Right,
of how
and,
you would
and in some ways,
explain not
right.
just
So
yeah.
So sometimes we think of topology in geometric terms, and the important thing to say here, the reason why this is not geometry is because we never talked about any distance or any angle or anything like that, or any measure of things, right? In that sense. And
Right.
it's all to do with overlaps, for example, or subsets, the subset operation or something like that. That's why it's just topology. But in particular, it's not even all of topology. As I said, it's a very particular view of topology that comes through the subject called cohomology, which is the consistency requirements on real valued function, in this case, real valued or 0, 1 functions in the interval 0, 1, on the sets that we're interested in. Anyway, but
And maybe
thank you.
one way to think about what's
Yeah.
going on in those diagrams that Ted was showing earlier, the ones that look like a triangle or really a tetrahedron, is you've got these people, and the people are sitting at the corners. And what the lines are representing, what the segments are representing, is whether the people have certain kinds of things in common and whether they're able to communicate with each other in certain ways. And one way to think about what the topological structure is representing is, if each of these people are able to communicate with each other in certain ways, are they connected enough that they can kind of distribute information around such that they can come to a common viewpoint or not?
Mhm.
And so what those diagrams are representing are the connections among the individuals. And then the question we're asking is, how connected do these individuals have to be to each other for the information to get where it needs to get so that they can all come to certain kinds of agreements? And that's a kind of way of looking
Or
at
or as an
Everything
obstacle, like
both of
how
you
disconnected do they need to be in order for them to
Yeah.
not be able
to
to? That could be
impede
hard.
the
Right,
transfer of the
right.
information. Right. Yeah.
And in connection with what both of you said, some of the earliest parts of topology were historically Leonard Euler solving the Königsberg Königsberg bridge problem. And so graph theory and map coloring, they're all topological issues. And the word topological has the same prefix root as topographical. And so then you're talking about mapping concepts in your case, mapping connections between agents and things like that. Whereas topographical is mapping connections between countries, boundaries between countries, and so forth.
Yeah.
So people who want an intuitive idea about topology related to this, if you're talking about connections, then graph theory is a good place to go for helping them have an idea. But I wanted to ask something related to that. So that's part of the reason I brought up that connection. Speaking of connections, in your description today, it seemed to me like the use was mainly related conceptually, not technically, to undirected graphs. But is there a sense in which what you're doing can be refined to include directed graphs? And then
I like that question very much, Matt. And honestly, it hadn't occurred to me before as a possible future direction, because we're only looking at overlap as the interaction that's clearly commutative. But in reality, the thing we're trying to model, which is, the opinions of people, I wonder, and Mike, I'm now asking it as a question to you as well, if something analogous to this may have arisen in the philosophical literature. I can imagine interesting mathematical structures to model it. The idea where, I might think I agree with you on something, or that, and that you don't agree with that statement that I agree with you. In other words, you
Yeah.
think we're disagreeing.
We're
and you
getting
think
into
you're
the meta language stuff that I was
Well, you
talking
were the
about
one who
earlier.
started it, Matt. So don't get. But is there something where, in other words, it's not a commutative operation? This notion of whether we're agreeing or not.
There are two contexts in which that kind of thing comes up. Um, in these structures I mentioned earlier that are known as accessibility relations, you can have accessibility relations that are non-symmetric, right?
Mhm.
And so you can have one state of the world A is accessible to B, but B isn't accessible to A. And when you're transferring information or probability distributions along these accessibility relations, those can be unidirectional. So there's some work on that. And then, of course, there's the directed acyclic graphs that all the probabilistic causal theorists do, but that's a very, very different setting. But those are the only two things I can think of. Yeah.
Yeah.
Mhm.
And by the way, I sat in part of a class with Robert Page here at S&T when I was a faculty member. And he taught this class on graph theory and epidemiology. And it involved, it was a representation of Bayesian inference for epidemiology. You might want to look there for some other examples. You mentioned metallurgy, but some other examples that might be amenable to your approach would be from epidemiology. He used a textbook, but I don't remember who wrote it. You might want to look that up. Yeah. So graph theory and epidemiology, or you may have heard of it already. I don't know.
Okay, so I want to first of all thank everyone,
Yeah.
and maybe look, we can wrap the live stream, and if people want to stick around for a couple final comments in the Zoom, that's fine as well. So thank you very much, and we look forward to seeing you in a couple of weeks for our next relatorium. Look out for the announcement. Thank you.
Thanks, everyone.
And you can end the live stream.
Yeah.
Okay. I do think, actually, in terms of, now you were talking about epidemiology, that's I mean,